Hello everyone, welcome back. So now a second group problem. So as always, grab someone with you. Currently I have my little traveling gnome with me and he's going to be helping me on this problem. But you can have your own little, avatar to assist you. So what do we have here? At a temperature of 40 degrees Fahrenheit, a 0.08 inch gap exists between the ends of the two bars shown. We have bar 1 is aluminum alloy, okay, with a particular thermal coefficient. And bar 2 is stainless steel, with its own coefficient of thermal expansion. We also know the supports at A and C are rigid, which means they will not move and they will not change. So what do we want to find? Well, we want to find the lowest temperature at which the two bars contact each other. Obviously, if you get too high, they're just going to be trying to crush each other. But what's the lowest temperature where they will still touch? So, pause. Take a moment, think about this, and see what you come up with. It's going to be a single equation, and you're going to have to solve for temperature. Shouldn't be too hard. But the big thing you need to remember is use temperature change in most of your equations for thermal strain. I'm not asking for temperature change, I'm asking for the lowest temperature. So, look it up, see what you find, and then come on back. So 3, 2, 1, okay, you did the problem, you succeeded or you failed. Either way, I'm not judging, I'm just a video. Let's jump into it together though. So first off, we need to write expressions for the temperature-induced deformations, and we're going to set this equal to the 0.08 inch gap. Okay, so we have our coefficient of thermal expansion times our change in temperature times length 1, because deformation is going to be equal to our thermal strain times the length, and our thermal strain is going to be equal to the coefficient of thermal expansion times the change in temperature. Change in temperature will be the same for both. Their lengths and thermal coefficient expansion will be different from both, but we know all the rest of the information, so we should be able to write this out. So we know that when they're both at the proper temperature, the sum of their deformations will be 0.08 inches. And so knowing that, we can then solve for the change in temperature, which is going to be 77.821 degrees Fahrenheit. So it takes a lot of temperature there. So since our initial temperature is 40 degrees Fahrenheit, the temperature at which the gap will be closed is 117.8 degrees Fahrenheit. It sounds kind of like some sort of like Bond villain, death trap. Mr. Bond, as the temperature changes, you shall be crushed by these two steel pillars. So, okay, if you're a Bond villain, please don't do this. That sounds like a terrible way to crush somebody. You know what? Just don't be a Bond villain. Don't be a Bond villain at all. Try to be James Bond. That'd be pretty cool. If you need an engineering professor to be a sidekick, I would be happy to volunteer. Okay, well, we've done this. It wasn't as hard as you probably guessed it would be. So I hope you liked this example. I hope you learned something. And I'll see you all next time. But before you go, remember, all we did here was we took our thermal strain equation and we figured out what the deformation was from that, and then we added those together to get the gap. And then from that, we calculated the temperature. The biggest thing you needed to remember was that they had the same temperature. Everything else you knew, but if you started saying, well, there's a temperature 1 and a temperature 2, you can't solve it. So don't forget that. Thank you all for listening, and have a wonderful day. Bye-bye.